and welcome to another session of Semiconductor Physics. Now, in the Brainware University, we teach to the first year engineering students this topic of semiconductor physics, as you know. Now, as a part of this, I am Dr. Shomujit Sharkar from the Department of Physics, is going to have a discussion for next few minutes about a basic topic of semiconductor physics, which is actually included in the module 2 of this syllabi, and it's called free electron theory. So the idea of this uh, presentation or lecture is to introduce to the students, or to you rather, about the basic idea of semiconductor uh, physics, but not exactly semiconductor, rather the metallic properties. So before going to semiconductor, we will understand first the properties of metal. And when I say properties of metal, it's mostly the electrical properties and maybe some thermal properties as well, which we will try to explain using some very basic model. And one of the very fundamental, or rather most popular and very simple model, is called Drude model, which will come in next few slides, and we will explain it how it can help us to understand some basic property of the metals and where does it fail. Of course, because it's a simple model, we should not expect that every property of metal can be explained using this model. So let's begin. Now, this free electron theory was first like proposed by Paul Drude. Paul Drude was a German physicist. So, of course, after his name, this model is called Drude model. Now, this particular model only considered the classical theory of physics, and therefore also sometimes it's also called classical free electron theory. Remember, this is a very subtle point, and we should remember that this model, when proposed, or this model is entirely based on classical theory. There is no quantum theory involved at all, and that is why it's mostly known in two names. One is called, of course, Drude model, and the other one is called classical free electron theory. Now, before going to classical free electron theory, let us try to understand the idea of atom. Now, this particular model was introduced to the scientific community way long, around 1900. At that time, we didn't have the idea or information about how an atom looks like. Later, of course, with the advancement of science and different theories, now we know a very accurate picture. But remember, when Paul Drude proposed his theory, there was not much information about what is actually, how does an atom look like, or what is inside its atom. Now, the basic idea what we had is that at the center there is a nuclei, which mostly consists of protons. So this is the nuclei part, and then there are few electrons that are revolving around the nucleus, close to the nucleus, which we term as core electrons. So we call them as core electrons. And then there are few electrons which are moving around those circular orbits. If we consider, let's say, Bohr's model of atom, then those electrons that are lying outside or far from this nucleus, we term this as free electron or valence electron. So now on, whenever we say electron, actually we will mean this valence electron or the free electron. And then the other two, that is together this nucleus and the core electron, these forms ion core. So these ion cores are positively charged and they are immobile. That means they are fixed at their position. So why they are positively charged? This is a very good question that we should ask ourselves. And that is because we know that in an atom we have equal number of protons and electrons. And since both electron and proton they have the same charge, so overall an atom is neutral. Now when we consider this ion, we have all the protons inside the nucleus, but we don't consider all the electrons. We only consider a fraction of it, which we term as core electrons, because then the rest we call as valence. Therefore, this ion has more positive charge because it has more number of protons than electron. Therefore, it has more positive charge overall. That is why these ion cores, these are positively charged cores, and they are fixed. They cannot move. That is why we are calling them immobile. So they are fixed. And then we are left with those valence electrons, which we term as free electrons. Now these free electrons, they move throughout the metal like it's a sea, and there are numerous number of electrons. Now when we say numerous number of electrons, how do I say this? So suppose, let us consider an example. Let's say sodium. So sodium has 11 electrons. Now if we go back to our 10 plus 2 chemistry class, physical chemistry chapter 1, where we learned how to write the electronic configuration of the electrons in an atom. So these 11 electrons, we can arrange them as 1s2, 2s2, then 2s6, and 3s1. So let's forget about this 3s1. Then this 10 electrons, that means 1s2, 2s2, 2p6, altogether these 10 electrons can be considered as core electrons. Then we consider that the last one, that is the 3s1, that poor guy as the, or maybe not the poor guy, maybe the lucky one, because it's not bound to anyone. It can freely move everywhere throughout the metal. So it's like there is no rule. It's like that electron is saying that my life, my rule. So it can move throughout the system, and this electron is called free electron. Now suppose we have 1 mole of sodium. If we have 1 mole of sodium, there are Avogadro number sodium. What is Avogadro number? Order of 10 to the power 23. 10 to the power 23. Now each atom contributes 1. So how many free electrons in 1 mole we can have? 10 to the power 23, which is like we cannot be able to count. So that is why we say that it's a numerous number of free electrons, and these free electrons are moving throughout the system, and that is why it's called a sea of free electrons. It's like after a torrential rain, the whole street is now waterlogged. So it's like we say we are in a sea, although we are not in a sea, of course, but we say this. Exactly something happens inside the atom. I mean, that is the idea. At least at that time, 1900, we had that these ion cores, they are fixed at their position, and there are free electrons, moving. This is the basic idea. Good enough. Now, what happens? If we look this whole picture, then essentially we can now consider a metal as like few fixed centers, like fixed balls. They cannot move. They are fixed at their position. Then there are free electrons like small marbles, or I mean like tiny spheres, classical particles, sphere. Let's consider them as sphere. And they are moving randomly, erratically everywhere. There is no rule. They are moving like, it's like someone, like a small kid running his or her bicycle on a free street. Like there is no traffic. It's like In your neighborhood, there's a freeway. On the freeway, there is no traffic, no car, nothing. And all the kids of that neighborhood are allowed to ride their bicycle. And they are moving everywhere with joy. These free electrons are left. So this is the basic idea. So now, based on this basic idea of atom, Paul today in 1900 posed his theory, which now we call as today's theory, or in other words, classical electron theory. Now, Drude assumed few assumptions. There are few assumptions. Now, these assumptions that we should remember. So, let's go into that. So, what is the the first thing that Drude assumed that electrons are moving freely throughout the metal and no force is acting on the electrons. Now, again, when we say electron, these are the free electrons or those valence electrons. Okay. Now, when we say no force, this no force means there is no force acting between two electrons as well as between an electron and an ion core. That is very unusual. Why this is very unusual? We will come in a minute. Just keep your patience. I will walk through you. So, the first idea is that electrons are moving freely throughout the atom and there is no force acting on the electron. That is why it is called free electron theory. Why it is say again, please try to emphasize, or I mean like note it down. That's why this is a free electron theory. Why this word free at the beginning? Because the electrons do not experience any force whatsoever. There is no force acting on the electron, the metal. That is what this model means this Drude's model assume. That's a great simplification, maybe a bit risky, but again, using these very simple assumptions, this model can do some wonder. It can explain some of the properties of the metal accurately, and that's surprising because we are considering very simple assumption and still we are getting something which is really, really good. I mean, when I say really, really good, means out. Now, electrons move randomly in absence of an electric field, and they collide with each other and with ions. So that is what is going to happen, because if electrons are moving everywhere randomly, then they will collide with each other, or collide with those fixed ions. This is gonna happen. There's no. The average distance traveled by an electron between two successive collisions is called mean free path. So what is mean free path? This time we should remember mean free path. What is mean free path? Mean free path is the average distance. Please do remember that we must mention this word average. This is the average distance traveled by an electron between two consecutive or successive collisions. That means two collisions that are happening next to each other. So like collision 1 and collision 2, or collision n and collision n plus 1, or collision n minus 1 and collision n. The average distance between two consecutive or successive collisions is called mean free path. Usually it is denoted by this Greek letter lambda. Lambda. Now what is the unit of mean free path that we should remember? The unit is meter because it's a distance anyway. It's a distance. So there's a unit is meter. Similarly, the average time interval between two successive collisions is called relaxation time. Once again, please note that we must mention while writing answers and etc. Average time. This is not just the time. That means we measure this time for several such instances and then make an average. So the average time interval between two successive or consecutive collisions is called relaxation time. Relaxation time. Again, what is the unit of average time? Of course, it's second, because anyway it's time. So these are the very basic idea that we should remember, and then we will move to the assumptions. What are the assumptions that today assumed about? So the first assumption is that electrons move along a straight line between collisions in absence of any electromagnetic field. Fine. So between two collisions, suppose there is a one collision and here is the second collision. So between the two collisions, the electrons move straight line. Electrons do not apply any force on other electrons, and the effect of electron ion interaction is also equal. This is very, very interesting. Why? Because electrons are negatively charged. That means. So from our 10 plus 2 physics idea, or even at 10th time, what we know is Coulomb's law, that if two charged particles are of same charge or same polarity, that means either they are plus or both are minus charge, then they will repel each other. And if they are of opposite polarity, then they will attract. This must happen. This is what we learned at the very best. And then this model, do they assume that, okay, let's forget about this interaction. We keep all the electrons as free. And when I say electrons, these are free electrons. That means those valence electrons. Those valence electrons, that is the electrons that are moving, orbiting at the very far orbit from the nucleus. They are being in a circular orbit far away from the nucleus. So this assumption is actually a very important yet very unusual assumption that we should remember. This is unusual. This goes against our general understanding. This assumption goes against our general understanding. So please do remember that there is no force acting on an electron. So electrons are moving freely, and that is why this theory is called free electron. Now, assumption 2. What is assumption 2? Assumption 2 is that the probability of collision per unit time, that is 1 over tau. What is tau? Tau is that mean free path. This is independent of position or velocity of electron. That means, do they assume that whether the electrons are moving with a high speed or low speed, doesn't matter. Probability or chances of collision remains the same. This is also against our general understanding. Why? Because suppose I'm riding a bike and I'm riding the bike recklessly without following any traffic rule with a very high speed, and there is another person who is of course a responsible citizen, follows the traffic rules, drive his or her bike at a regular speed with all protective gears, maintaining the traffic norms, traffic rules, that is, and all that. Now, of course, for my case, there is a high chance that I will commit some accident. That means I will get collided with some. Right, very high chance. Again, for the other rider, who is the good person, let's say, following the traffic rule, also there is chances of collision, but the chances are less, much less. This is the basic idea. But Rude said no. The probability remains same. The probability of collision remains same, no matter what is the speed of that electron. So whether electron is moving very fast or slowly, it is close to another electron or far away from an electron, doesn't matter. Probability of collision remains the same. So this assumption is also a very simple assumption, yet unusual, because that goes against our general understanding. Now once again, here we must remember, when I say this tau, which is mean free path, just few slides before we say that this tau is called mean free time or relaxation time. This is the average time interval between two successive collisions. And then there is another one, that is the third assumption, which will be the last topic for today. The third assumption is that after a collision, electrons move in random direction with a speed appropriate to the temperature of that region. That means that what will be the speed of an electron after collision does not depend on what was the speed before the collision. That means the previous memory is completely ignored. So after every collision, an electron emerges with a new speed, which is independent of its previous history. But then it only depends on the temperature of that region where that collision happens. The regional or local temperature. If higher is the temperature, then the electron will have a high speed after collision. If the temperature is low at that region, then the speed much less. So that is the third assumption. So these are the three assumptions that we should remember. And then in our next class, we will carry on from this further. So for today, what we learned, that what is Jude's model, on which theory it is based on, what are the basic assumptions, and few basic definitions. So the next class we will start from knowing few more definitions. For example, already you can see here is the electrical conductivity. So we are going to estimate the expression or value of electrical conductivity of metal using this Jude's law. That will be the task for the next session. So thank you very much for your time, and see you in the next session. Goodbye.